In our second section of nuclear chemistry, we're going to talk about half-life. So right now we know about 2,000 different nuclei. So when you look at the periodic table, there's obviously not 2,000 different elements, but 2,000 different nuclei. So remember we talked about carbon, how most carbons are carbon-12, but there's a few carbon-14s out there. So that's 2 out of these 2,000. Approximately 260 of them are stable and never decay. They don't change. Like carbon-12 stays carbon forever. It even becomes so compact that it turns from carbon, like coal, into diamonds. Okay, it does not decay. But the rest of them will decay and change with time. The stability or the resistance to change depends on its neutron to proton ratio. So remember, ratio is just a fraction. So if we take the number of neutrons and divide by the number of protons, that's our ratio. If we plot a graph of number of neutrons versus number of protons for each element, we get this thing called the band of stability. And if you notice, there's like these little lines here where they're all connected. These are nice and stable here, but then every once in a while you have these guys that are off on the side here. These guys are the unstable ones that want to decay into something else. This line right here is the 1-to-1 ratio where your number of neutrons and number of protons are exactly the same. For elements with low atomic numbers, so anybody below 20, like the ones we're most familiar with, carbon, oxygen, all that good stuff, the ratio of neutrons to protons is almost exactly 1. So let's think about that carbon that we talked about. Carbon-12 has 6 protons and 6 neutrons. So if I was to divide the neutrons and protons, like we had before, 6 neutrons divided by 6 protons, it gives us 1. And if you look, these are really close to this line of 1-to-1. Okay, these guys down here are nice and stable. They don't decay into something else. They don't undergo radioactive decay. But if you notice, the higher up we go, how this curves up and it gets away from this 1-to-1 line here. Once we add more stuff on there, stable nuclei have more neutrons than protons. So the ratio of these is closer to about 1.5 for some of the heavier elements. So if we take something like lead, Pb, he has 82 protons. That doesn't change unless you become something besides lead. But to make 206, that means he has 124 neutrons. So when we divide these, we end up with about 1.5, which is much bigger. But that allows them to be stable and not decay. The neutron to proton ratio is very important because it tells us what type of decay occurs. So if your neutron to proton ratio is different, it's going to tell you if it's alpha, beta, or gamma decay. All nuclei that have an atomic number greater than 83 are radioactive, meaning that they are not stable. So when you look on the periodic table, anybody with a number over 83 wants to decay into something else. Ever wonder why some atomic masses listed on the periodic table have parentheses around them? Like, break out your periodic table right now. Some of them have just actual numbers like lead and bismuth, but then one like polonium has parentheses around it. That's because all of these guys are estimates. We don't actually know what radon's atomic mass is, but we know it's very unstable, and we know if it goes through alpha decay what it looks like, we know if it goes through beta decay what it looks like, and if it goes through gamma decay what it looks like. So based on that, we can estimate, like work our way backwards to what we started with. So half-life is the time it takes for half of the nuclei in a radioactive isotope to decay into other products. So remember, if something's unstable, it wants to change. When we talk about half-life, it's how long it takes for half of those nuclei to change to something else. So for an example, let's say I have 20 atoms of radon. It's radon-222, and the half-life is 4 days. How many atoms remain at the end of 2 half-lives? So if I start at time 0, I have 20 atoms initially. After one half-life, which is not 1 day, but 4 days, because that's our half-life, how many would I have left? Hopefully you said 10, because it took half of them. And then after another half-life, which isn't 2 days, but instead a total of 8 days, I would end up with 5 atoms. So at the end of 2 half-lives, or after 8 days, I would have 5 atoms of this radon-222. We can draw a nice little graph of it. We'll draw some more graphs tomorrow in class. Hopefully you remember back from Math 8, this is an exponential curve. And in an exponential curve, it starts up high and then it goes down quickly. So as we can see, if I start with 100 of something, I'd get 50, then 25, then 12.5, and we could keep on going on and on and on and taking half every time. So for this example, this is carbon-14. Its half-life is 5,730 years. So it takes almost 6,000 years for half of a carbon-14 sample to decay to half. However, very seldom do we count actual atoms. It's very difficult to do. So usually what we talk about is mass. So I have some mass of something. How much mass would I have left after a couple of half-lives? So let's do a problem. Carbon-14 emits beta radiation and decays with a half-life of 5,730 years. Assume I start with a very tiny mass, so 2 times 10 to the negative 12 grams of carbon-14. How long is 3 half-lives? And then, how many grams will remain at the end of these 3 half-lives? So, question A, let's figure that one out first. So, I need 3 half-lives. 1 half-life is 5,730 years. So, to figure out 3 half-lives, all I got to do is multiply this by 3. So, 3 times 5,730, we can break out our calculator. We'll end up with 17,190 years, so a pretty long time. And then the second question says, how many grams of this isotope will remain at the end of 3 half-lives? So this takes the 17,190 years, but we're only going to cut this in half 3 times, because it's 3 periods of time that it has gone through that half-life reduction. So we can do this a couple different ways. We could take this 2.00 times 10 to the negative 12 and multiply it by a half, multiply it by a half, multiply it by a half. So here's 1 half-life, 2 half-lives, 3 half-lives. Type that into our calculator and it's going to spit out a nice tiny number. We're going to end up with about 2.5 times 10 to the negative 13 grams of that substance after 17,000 years. So we got one more problem to do. This one talks about manganese 56. It's a beta emitter with a half-life of 2.6 hours. So the beta part isn't really important for what we're doing because the questions that you're going to ask is how many half-lives will the sample go through at the end of 10.4 hours? And then what mass, if I start with 1 milligram, will be there at the end of this 10.4 hours? So this one's a little different than the last one. If my half-life is 2.6 hours, how many have gone by in 10.4 hours? So this time I don't want to multiply, but instead I want to divide. So if we do 10.4 divided by 2.6, that gives us 4 half-lives. So that means it has been cut in half 4 times. So then the next part says, I start with 1 milligram, how much is left after that? And I'm going to take that 1 milligram and I'm going to multiply it by a half 4 times. So 1, 2, 3, 4. Now when you do that, you just throw it in your calculator. You end up with 0.063 milligrams are left. Make sure you write down any questions you have. We can go over them in class. We're going to do a lab tomorrow and watch a little video on half-life. Enjoy your night.